And we did not have homework for today, correct? We talked about stacks at the end of the class, and I probably linked you to the Towers of Hanoi thing and said, go take a look at this thing, and we'll start talking about it today. Okay, so with that being said, did I start writing anything with our stack? It doesn't look like. I've just talked about it, right? All right, so what we're going to do is, I mentioned last time that a stack is a last in, first out queue. So it's a linked list that basically supports only add front and remove front. And it also would have another function called get front. These are called push, pop, peek. Push puts a new element onto the top of the stack, the front of the list. Pop removes something from the top of the stack, the front of the list. And then peek shows us the thing that's at the front of or at the top of the stack, or the front of the list, but does not actually remove it. All right. So those are the three functions. We can go ahead and implement this in terms of our linked list. Oh, actually, I do remember I was showing you the inheritance thing at the end of class last time, and I think I posted up. Yeah, here's our stack code. Yeah, so just reviewing here real quick how this works. A stack is implemented in terms of a public linked list. So this is how we make a stack inherit from linked lists. So this is kind of like in Java saying stack extends linked list. This security thing ahead of this describes how the fields get passed through. All right. So by making this public, we have access to anything that is public we have access to everything in linked list. So all of this stuff. By making it protected, let me just make sure that that's a true statement that I'm saying here, because if I make this private, then I won't have access to the stack. Okay, let's refresh the page and see if I can get a keyboard working.
Like do the forward this thing. I think you put your link, it like assumed it wasn't private.
Oh, like I'm not logged in.
Yeah.
Interesting. Okay. Thank you. Let's just switch it to private here real quick. I am using this out here in main to call push, but push are things that I wrote inside of stack. So push, pop, peek, these are all public functions, but they're written in terms of our linked list functions. So by making this private, I don't think we're going to have access to our linked list functions. But let's see here before I specify that. Yeah, inaccessible within this context. So we don't have access to display. And the rationale is that display is not a function from stack. It's not one of our public functions from stack. It's actually a public function called from linked list, but we brought linked list in as a private member. So we don't have the public things from linked list exposed publicly outside of stack, since we extended it privately. If I make this protected, that would be the next level. Only things that inherit from linked list would have access to this stuff. So I think I can, if I say protected there, it should still fail for the moment. But then I'll fix it by showing you one other thing. Yeah, so still fails with the same error, but now I'll go into stack here. I'm sorry, linked list. And I'm going to create a new section called protected. And I'm going to put display in that protected section. Which means it's available to linked list as well as things that are children of linked list directly. So I believe by making the display function protected, I now will be able to externally, outside of stack, be able to use stack to call that protected method. Where I wouldn't have been able to use stack to call add front, for example. I can call push because I wrote push inside of stack. I wrote it in terms of add front, but in this case, I am inside of the stack class, not accessing it externally. So let's make sure that this works now that I made that display a protected function. So it tells me it's protected, but that will give me access to it internally. So I guess I just need to make it public in order to have access to it. Well, I had it public before. Yeah, so it's not going to really even make sense to have it protected. I can't come up with a good example of when I'd want something protected in terms of external use. So bottom line is, we would probably say that in most cases, we would extend the class publicly, because I don't think if I leave it off like that, I don't think it works. Yeah, because when I leave it off like that, the default is a permission called friend. And so that's like package level in Java, and that also doesn't give me access to it. So I would say for right now, always inherit publicly, because this effectively says treat linked list in the same way that linked list was originally written. Don't lock it down in any sort of extra way. If something was public in a linked list, it's now also going to be public from stack. So with that, I'll be able to call display, even though I didn't write display inside of stack. Instead, display came from me inheriting from linked list. All right, so there's my push. Did I write pop already? I think I wrote pop already. I just haven't tested it. All right, so pop, remove something from the list. So I'll go ahead and call that. So I'll say cout s pop. And then I'll say s display. So we should get the 3 printed out, and that will actually remove it from the list. And when we display it, we'll see the 2, 1. So there's the 3, the value I popped off, and here's the resulting list, 2 and 1. All right, and if instead of pop, I say peak, which works a lot like pop, except it doesn't actually remove it from the list, I'll get the 3, but when I display it, I'll get the entire list because that 3 didn't actually get removed. Make sense? All right, so we should see that a stack is much simpler than our full functioned, knows how to do everything linked list. And if you were writing a stack from scratch, you would only need to write it in terms of add front, remove front, and get front effectively. So we could probably say those were some of the easier functions to write. When it came to our linked list, we didn't have to worry about a tail pointer. We didn't have to worry about a previous or next node. We didn't have to worry about traversing the whole list to a certain place to put something somewhere in the middle. Just operating off the very front of the list is kind of our simplest version of a linked list. All right. Now, having said that, I'm going to go back to our Towers of Hanoi. We want to try to create a representation in C++ of this game. So what I want us to do is visualize that each of these towers, so the rules of our goal of Towers of Hanoi is to get these disks over to this far right tower in the same order as they are here, because Tower of Hanoi has rules that say a larger disk cannot go on top of a smaller disk. So that's an illegal move. I can put a smaller disk on top of a larger disk though. So ultimately you just keep playing this game. We're already pretty inefficient on this particular pass through, but that's okay. And we've won by getting all the crap over to the other side. Okay, so each of these guys is going to be representative as a stack, right? But it's a stack whose push method has a little caveat. When I go to push something onto a stack, that push only is allowed to happen if the thing that's currently at the top of the stack, the peak of the stack, has a size that is larger than the thing I'm trying to push on, or the stack is currently empty. Make sense? So the stacks have special rules to it. I can't just push or pop from the stack. I need to get it onto the stack in a, what's called a reasonable enough way following these rules. Now, instead of us having numbers, like right now we have our linked list or our stack of values is a stack of ints. Now we're going to have a stack of these disk objects, okay, where maybe a disk has a value. So maybe this has a value of 1, this has a value of 2, this has a value of 3, kind of representing the size of the disk. Makes sense? So we have stacks of disks. And ultimately, we want to let the user, maybe we show a text-based version of this board. Maybe this is tower 0, tower 1, tower 2. And we say, enter your source tower. So if I want to move from tower 1, so I'll say, tower 1 is my source tower. Destination tower is tower 0. It will then try to make the move from the top of tower 1 to push onto tower 0. And if it works, the move gets successfully done. If it doesn't, it reverts. So in this case, it works. We've done that. Source, tower 2. Destination, tower 0. That's an illegal move. So it's just going to revert back to what it used to be. Source, tower 2. Destination, tower 1. Source, tower 0. Destination, tower 2. So on and so forth. Make sense how this works? Okay. So what we need to do is we need to go back and reinvent our stacks a little bit. So I'm actually going to start another project, and we're going to call this guy Towers of Hanoi. And we're going to implement our stack. I'll actually probably just go ahead and rewrite it just as a simple stack, so we don't even need to bring in a full linked list with us. Just have a stack of disks. But we want to design what these guys should look like. So Towers of Hanoi. A tower object is a stack of disks. A disk has a payload that is associated with the size of the disk. So we have a couple of ways we could look at this. We could say that our tower, just like a normal linked list, is a collection of nodes, and those nodes have a payload that would be a disk. We could think of it like that because that's what our current linked list is, right? Our current linked list is we have a linked list of ints. Well, really, the linked list maintains a linked list of nodes where those nodes are buckets that know how to hold ints. All right, so we can say that a disk has a size, but a disk also knows about the next disk and the previous disk. Or we can say that a disk lives inside of a node. The node is what links itself to the guy before and the guy after. But ultimately, the disk is the payload of that node. Either one of those are viable solutions. We might say, well, which one makes the most sense? Well, when I remove this guy from a tower, when I pop it from a tower, if he was enclosed in a node, I just got rid of that node, didn't I? I no longer need to link to this guy or anything like that. So I got rid of that node. And when I go to push him onto the next tower, I'll have to generate a node that will hold him to put him onto that tower, unless I have the node travel from point A to point B. As opposed to if I take this disk and the disk isn't enclosed in a node. Instead, the disk is our node. I remove this disk from here, disconnecting his next node and his previous node. In this case, it's probably always just a next node, right? Good for a simplified linked list. So I'll disconnect his next node. So he's no longer linked here. He's in limbo until we finally drop him onto his destination tower, where if it goes onto this destination tower, we'll add him to the front, which will set his next node to this next guy there. So I think we can say that we're going to have a stack of disk objects, not a stack of nodes that each hold a disk object. Because really a disk object is another name for a node that holds an integer. Does it make sense? That's what we've been writing all along. We've been creating nodes whose payloads are integers. And I'm saying maybe this guy has a payload of 1. This guy has a payload of 2. This guy has a payload of 3. Just those numbers happen to correspond to the size of the disk that it's representing. So a disk has a payload that's associated with the size of the disk. As a display method that maybe shows a number of equal signs representing the size. So maybe a single equal sign for the disk that's 1, 2 equal signs for the disk that's 2, 3 equal signs for the disk that's 3. If you want to make it bigger, if you want to go 2, 2, 4, 6 or something like that, you can do that if you think that makes your tower look better. I wouldn't spend too much time, doing like indenting and stuff like that to make your towers look perfect. Left justified type stuff, even a tower right on top of another tower, right on top of another tower, instead of having them visually created on the screen where we have a tower next to a tower next to a tower. I think that becomes maybe a little bit more tedious to create when it really has nothing to do with logic other than just making text show up on the screen in a reasonable way. You can decide, you know, what you want to focus on when you're doing it, but I think the stack stuff makes some more sense. All right, so let's go and start making some of these pieces. So I'm going to create a new project. And we're going to save this guy. We'll call this guy Towers of. Apparently, I have to call it Towers now. Do I have the opportunity to change the name of that? It's called Towers. That's going to be what we're going to call it. And Towers is going to have a disk object associated with it. So we'll go ahead and create that. So we'll create a new file. We're going to create a disk. And this is going to be flash disk. We'll have a private section here where we have an int. I'm going to go ahead and call it the size. This is the size of the disk, even though we're really just creating new names for things that we already have done. This is a node that we're creating here, and the size is the payload of that node. All right, we're just trying to make the names match up to the problem we're solving. All right, so a disk has a size. And we'll have a function called display. Now a disk also needs to know about the next disk in its particular stack, because this is a linear linked data structure. All right. So now we're going to go and implement this dude. We'll probably come back and add some stuff later, but we can start by implementing them. So we're going to create our, what I need to name this guy disk. Hey, this is disk.hpp. Then I'm going to create a new file, disk.cpp. And we will include disk.hpp. Got to go to disk HPP. We need to remember to have our constructor for this guy, right? So this guy is going to be a disk. And when we first create a disk, it's going to take in a size. So we'll go ahead and write this constructor. All right, so we're going to say this size is equal to size. And we'll say this next disk is equal to, is it all caps? Is equal to null. So when we first create a disk, I go back to our picture here for Towers of Hanoi. When this guy comes into existence, he's not on a tower or anything. When he comes into existence right now, he has a size and he currently points to nothing. Make sense? Okay. And then we'll go ahead and create our display function. And let's see. Display is void. And this belongs to the disk class. And for our display function, we want to go ahead and build up a string representation of our disk. Like I said, maybe we do this with equal signs or something like that. So I'm going to include string.h, and I'm going to say using namespace standard. So inside here, I'll go ahead and create a string s, start off as the empty string. And I'll say for int I is equal to 0, I is less than size, I plus plus, and we'll go ahead and do 2 equal signs per size. So we'll say s is equal to s concatenated with 2 equal signs. So if the size is 1, its representation will be 2 equal signs. If the size is 2, its representation will be 4 equal signs. If size is 3, its representation will be 6 equal signs. All right. High-end graphics here for our game. All right. So that's what display is going to create. And then we'll go ahead in the end. For right now, we'll just output whatever that representation of our disk is. All right, so far so good. And we'll go ahead and test this guy real quick. So go out to main. We will include disk.h. We don't need standard IO. And we'll go ahead and create a disk pointer. D1 is equal to a new disk size 1. Disk pointer D2 is equal to a new disk size 2. Disk pointer D3 is equal to a new disk size 3. And then we can say D1 dot display, D2 dot display, D3 dot display. And we should get our 3 different disks visuals. Let's see, string was not declared in the scope. Give me a moment. Is it not string.h? Is it just include? Oh. We didn't write string.h. String.h is part of the C library. So you got to have those angle brackets around it, not the double quotes. Double quotes say, we wrote this, look in the current directory. Disk.h. Where did I write include this.h? In here? Oh, it's HPP. Oh my, I have so many typing errors today. I'm off my game. It's not the dot, it's the arrow, but we're going to say that I did this on purpose because, you know, these are all things that I've brought up, and when to use the dot, when to use the arrow, all that stuff. So remember, D1 is a disk pointer. So we actually need to dereference it to get to its display method. That's why we use the arrows here instead of the dots. All right, so that's the string thing. Isn't it include string like that? I don't think it's a capital S for string. Okay, we're good now. And we need to include our IO stream. All right, there we go. So IO stream is the guy that has the standard, that has the C out in it. string is the guy who has the string class in it, and both of those live inside of the standard namespace. All right, so you do this thing right here along with this thing, and now you effectively have Java style strings. That's this guy here, build up my thing. So I create my 3 different size disks and just tell each one to display themselves. All right, so now we want to go ahead and create our tower. Our tower is going to be a collection of disks that we can push onto the tower, right? So we'll create a new file, tower.hpp. And this guy, a tower will be a collection of disks. So our tower needs to know about the disk class. So we will include disk.hpp. So, and we put the double quotes around it because that's the class that we created. Then we're going to create a class tower. All right, and we're going to have in our private section here, we're going to keep track since this guy is going to effectively be a stack. He's a stack data structure that has some special rules associated with it. We're going to say that we're going to keep track of the top of the tower, the top of the stack, and that guy will be a disk pointer called top. All right. Now we're also going to have the ability to push something onto our tower. And he'll take a disk that we're going to push onto the tower. As opposed to in our previous linked list example, where we pushed on payloads. We pushed on ints and generated nodes around those. In this case, and then when we took something off our linked list or our stack before, we took the payload out of it and returned that payload. In this case, we're actually returning the physical disk with its size and everything. So we're passing the actual construct that lives on the stacks in this case, as opposed to the thing that lives inside of that construct. One's not better or worse than the other, it just happens to go down with the kind of problem we're solving here. Where before we were just storing a bunch of numbers, nodes were the means by which we stored those numbers because integers can only hold a value. They don't have next nodes and previous nodes and all that stuff. In this case, our game requires not the size that's inside of the disk. It requires the entire disk. All right. And the fact that that disk knows about its size is utilized by the display method for that disk. All right. So when we push something onto the tower, we will push the actual disk onto the tower, not the size of the disk, and have it generate a brand new disk. You could do that, but it'd be pretty destructive, right? If every single time you popped a disk off the tower, you extracted its size, and it's okay, we're putting it onto that one. Create a brand new disk down there that's this size, and it went and did it. And as programmers, we could do that, but maybe it doesn't make the most sense for us. So we'll have push. We'll go ahead and have a disk pointer pop that will remove something from the top of the tower. And we'll go ahead and have a disk pointer peak as well that will show us the top of the tower without removing it. Because it might be nice before we push something onto the tower, it might be nice to just kind of look at the tower and say, is this guy going to work? Is it going to be cool for me to push him on the tower? I could do that, or I could just try to push him onto the tower. And if it comes back with a false or something, comes back with some sort of error, well, then I decide it didn't work. So we can, we'll get to that here in a few minutes. Well, you'll probably do some of it for your homework, but so you can decide how you want to implement that. But we're going to have this private section, then these guys are going to live inside the public section because we want to be able to publicly push pop peak. And then we need our constructor for this guy. So when we create a tower, he's initially an empty tower. And then we'll go ahead and push things onto the tower. All right. We probably also want a tower to be able to display itself. Show me the current state of a tower. All right. So this would be void display. So we'll go ahead and implement all these guys. And this is tower.cpp. So we'll include tower HPP. Oh, Ninja. All right. When we first create our tower, I'm gonna add one more thing to our tower that might be handy. Why don't we go ahead and keep track of the number of elements on it? Keep track of that count. So maybe we can even ask a tower how many discs on there. If the count is 0, that means we don't need to check any special rules. We're allowed to push the thing, right? So keeping track of an int count might be a nice thing to do inside of our inside of an individual tower. So in our constructor, we'll go ahead and set count. Initially equal to 0. And we'll set top initially equal to null. Plain Jane, fresh tower, nothing's on it. Well, did I not? Oh, here's, man, killing me here. This stuff goes inside the constructor. All right, so for push, when we add something onto the tower, I'm going to go ahead and treat the tower as a generic stack for right now. And then you're going to be converting it to a Towers of Hanoi style tower that follows those special rules. All right. So if I'm pushing something onto a tower, I want to effectively add to the front of this list, add to the top. All right. So we have our disk. Currently, our disk is keeping track of the size, but we also have our next disk. All right. So it's equivalent to our node from before. So we're going to go ahead and say d dot set, what do we call it? We need to give it that function. So under our public functions, we now need to teach a disk how to set its next disk. All right, so we'll add some abilities to a disk. Set the next disk, we'll set this dot next disk equal to whatever was passed in. So now in our tower, we can say D set next disk to this top. All right, so this new disk that we're pushing onto the tower will become the new top. Okay, so we wanted to point to the same thing top currently points to. And then we'll say top is equal to D. New guy comes in, make him point at the same thing top points to, then make top point to this new guy. Now he's at the top of our tower. Since we just added something, count plus plus. Okay, so that's pushing from the tower. Popping from our tower is going to require us to return the current value that's at the top of the tower. We'll say even if it's null. All right, so we'll create a disk pointer. Call this guy disk to return, and he's going to be equal to this top. All right, but now we want to ask the question, if this top is not equal to null, I think I showed you before, you actually don't need to actually ask if it's not equal to null. You could just say if this dot top. This asks the question, is this dot top equal to something? But just to keep it explicit for right now, we're asking the question, is this dot top not equal to nothing? That means if it is something, then what do I want to do? Well, I need to first set this top to be equal to this top. I need to get his next node, right? I want him to point to his own next node because I'm about to remove something from the front. So I need to go back into our disk. I need to write a function that returns a disk pointer called get next disk. All right, so we're going to teach we're going to teach a disk how to tell us about who comes next. Go ahead and write this dude. We'll return this next disk. All right, and we needed to do this because with disks, we had these guys in the private section for next disk. So we needed to give ourselves a getter and a setter for that. All right, so back to our implementation here. So we're going to set this dot top equal to tops next disk. And then we'll go ahead and say disk to return dot set next disk equal to null. And we'll say count minus minus. We're only going to decrement count if we indeed did remove something from our tower. If I didn't get into the if statement, that means disk to return is actually equal to null, which is fine. I'll just spit out a null value. Like, look, you told me to pop the thing from the top of the tower. The thing from the top of the tower was nothing here. All right. But we're not going to change the size of the count on the tower to be a -1 now. All right, that'll throw our count off. So only if we actually had something on there do we want to play the whole disconnect game and decrement our count. In the end, we'll go ahead and return the disk to return. For peak, we don't need to do any sort of disconnect stuff. So we're just going to return the current top. For display, for int I is equal to 0, I is less than this count, I plus plus, and we'll say disk pointer cur disk starts off at top. So we'll tell cur disk to display himself, and then we'll set cur disk equal to his own next disk. So we'll just run cur disk down our tower, telling him to go ahead and display each of our things on the tower. Okay. We'll go ahead and include tower HPP. Now, since tower HPP already knows about disks, I actually don't need to include disk there. Now I'll create a tower pointer. And we'll say T1 dot push D3. T1 dot push D2. T1 dot push D1. T1 display. I know I'm using the wrong dots again. These are arrows. Null was not declared in the scope. So in tower, null lives inside of namespace standard. Am I lying? It's null in all caps, isn't it? I don't think it's an IO stream. That's this guy's a function call. And it was an IO stream. No. Interesting. Okay. So there is our single tower being displayed. So for your homework, and I'll put this up on Blackboard, we're going to create a Towers of Hanoi game that will have you generate 3 towers and is going to have you move stuff between the towers, just proving that it functions. So basically allowing you to say, I'm going to pop something off tower 0 and put it onto tower 2. Right now, not following any of the rules of Tower of Hanoi. All right, so we're just kind of doing that very next step of getting that tower object created. Okay, so you'll have a collection of 3 towers and go from there. But I'll put it up on Blackboard and I'll see everybody on Friday, right? All right. Yep. Yes, Tech Talk tonight, 4 p.m. till 6 p.m. It is currently scheduled out for the Bluff. I think they're looking at an alternative location in case it ends up being too cold. But I think the sun's supposed to come out, so it'll probably be okay. But and that's Aurora WDC. There's an information sheet on it right outside in the hallway here on the thing. Highly encourage you to go to it. Also, the info meeting for CU launch is tonight at in the outside the makerspace in the business building. That's at 6 p.m. Free pizza, stuff like that. And that's an entrepreneurial competition thing. So I strongly encourage you to get involved in that. I put something up on Slack a week ago or something like that about that. If that's something you do want to do and you haven't already emailed Dan Sem, do that as soon as possible before they order their pizzas. All right, I'll see you tonight, probably.